Hello, everybody. My name is Raj. I'm going to be the presenter for this webinar. It'll be on the Test Lab Sound Power in Test Lab 2506, specifically in Test Lab Neo. That'll be the focus of this presentation. Here is the agenda for today's presentation. First, we're going to look at sound pressure versus sound power. What is the importance of sound power? What are some regulations associated with this sound power? Then we'll look at how to measure sound power based on sound pressure measurements. And then we'll have a demonstration of how to do the sound power calculations in Test Lab Neo, and we'll wrap up with some final thoughts. Sound pressure versus sound power. Now, in acoustics world, these are the two common terms that you hear, sound pressure and sound power. And sound pressure, if you want to know how loud a source is, for example, in this case, there is a source which is a speaker. There are actually two speakers. And if you want to know how loud it is, you typically use microphones to measure the sound. And when you do the measurements, you can place the microphone at different distances away from the source and at different locations around the source. And both the distance and the location, they do matter when you're doing the sound pressure measurement. So sound pressure measurement will allow us to measure how loud a source is, but it is very much dependent on where you are measuring and how far you are measuring from the source. Now, on the other hand, if you take the sound power, it is the total amount of sound energy that is radiated from the source. So it is independent of the distance you are measuring and where you are measuring, like the location you are measuring, because it's the total amount of sound energy radiated by the source. You can use sound pressure measurements to calculate sound power, and that will be the focus of this presentation. If you take the analogy of the sound power, suppose we have electric heater in a room, and heater will be radiating heat around the room. And what is the temperature at specific location in the room will be dependent on how close you are to the source, measuring the temperature using a thermometer, for example, and then also which direction, whether it is facing forward or backward, things like that. Sound pressure is something similar to that. It is like the measurement of the temperature around a heater. The heater we can consider similar to a sound source. And then if you take sound power, it is the total amount of heat energy. In the case of sound power, it is the sound energy coming out. The heat energy radiated from the heater is independent of where you measure the temperature. It is the total amount of heat energy coming from it, and that is measured in watts. And that is what the common rating that we see when we are in the market for any heater. That's what we look at. How much amount of heat energy can it make? And similarly, if you want to know what is the total amount of how loud something is, we want to look at sound power, because that represents the total sound energy coming from the sound source. Why is this important? Let's take a look at that. This sound power, it is commonly used in a wide range of industries because it is a measure of the absolute level of the sound energy coming from the source, and it is independent of the measurement environment it is being measured in. It is truly representing how much is the sound energy coming from a source, and that is why we look at the sound power. The sound power level is a term related to the sound energy, but it has been normalized with respect to a reference quantity. It is converted into a log scale and is represented in terms of dB. So sound power level is expressed in terms of dB, and that reference sound power is 10 to the negative 12 watts. So whatever sound power we have, we will convert that into dB using this formula. They are being used in wide range of industries. Like I said, the requirement comes not only from a legislation standpoint of view, where governments, they will say, hey, this is the level that is acceptable for this equipment. So there can be legislation for that. There is European standards for that. And also many a times, if you are in the product development of something like a dishwasher or a washing machine, you want it to be quiet and you want to design it such that the total sound power coming from it is low, and you can use that as a differentiator in the market. Dishwasher, especially if you think of it, there are some quiet dishwashers because in many homes they're inside the home in the kitchen, and you don't want them to be making too much noise. So sound power is a stringent requirement for the dishwasher manufacturers. You have to do engineering to be able to come up with that noise reduction such that there is not too much sound coming from it. And how do you know whether you have an engineered a good product is by measuring the sound power and comparing at different stages of the development and making sure that it meets the requirements that have been set for this market. The sound power is used in a wide range of industries, including home appliances, earth-moving equipment, automotive industry, handheld power electronics, and even in some things like data centers and all wide range of applications for this. And sound power, to measure it, there can be two different ways to measure it. One is called sound power based on the sound pressure, and also sound power based on sound intensity. Intensity is another quantity which is commonly used in the acoustics world. That is a vector quantity. It represents how much of sound energy is coming through a unit area. So it is a vector quantity. Unlike sound pressure and sound power, which are scalar, sound intensity is vector. Coming to the point of how do you measure sound power is that if you have a sound source and if you want to do the pressure-based measurements, you can place the microphones in the form of an array at different locations, and you have to spread them uniformly. In this case, this is a hemisphere arrangement we call, and you measure the sound pressure at each of these locations, and then you take the area into account to compute the total sound power of that source. There are ISO standards for this, ISO 3741 to 47, that help us to do these measurements. How to select the instrumentation, how to place the microphones, what type of microphones to use, and such. So that is the sound power based on the sound pressure. On the other hand, if you want to do the intensity based measurement, around the sound source, you create a measurement surface, like an imaginary measurement surface. You can create a grid like this, for example, and if there is a sound source, you are measuring around the sound source, you have to measure intensity at each of these grid points. You can take that area into account to calculate the total sound power. When you do this discrete point method for this sound intensity based sound power, that can take a little bit of time because you have to measure at each point individually. On the other hand, there is also a scanning method where instead of measuring at each of these distinct points, like a scan is done on each surface, once horizontally and once vertically, and you can use that technique also for sound power calculation. And there are ISO standards for that as well. ISO 9614-1 is for the discrete point method for sound intensity based sound power, and 9614-2 is the scanning method for using intensity for sound power methods. But today we are going to focus on the left side, which is the ISO 3744 and 3745 for sound pressure based sound power measurement. As I mentioned before, there are some regulations and standards that are available. And if you look at the big picture of all the standards, they tell us what are the products, who all needs to measure, and how to measure, what is the type of instrumentation, and here is a listing of all the standards. And what we are going to focus today is on the ISO 3744 and 3745. Let's focus primarily on the sound pressure based sound power measurements. So I'll give some introduction on how to do that. Then I'll show in TestLab Neo, I'll demonstrate how to do this various calculations. So ISO 3744. This is the standard that is commonly used across many industries to compute sound power based on sound pressure measurement. And the concept is that if you have a sound source, you build imaginary surface around that sound source. For example, in this case, there is a printer and we are building a hemispherical array around the printer with a lot of these sticking things, which are the microphones. They are pointed at a certain angle and pointing towards the center of the hemisphere. If we know the precise locations of these microphones and the ISO standard tells us where to place them, we can take the area of that hemisphere into account and compute the sound power from that. So this is an example of a hemispherical arrangement. Similarly, you can have a parallelepiped kind of an arrangement also. We'll see later there are different arrangements that can be made for this purpose. And the ISO standard helps us in choosing which arrangement we want to use. One of the questions that can come up is how many microphones to use for the sound power measurements. And there are some data quality metrics that are available that can be helpful in determining the density of the microphones that you need. You can see how much is the difference among the microphones. And then based on that, if there is too much difference, more than 3 dB difference among the microphones, then you know that you have to increase the density of the microphones there. Ultimately, what we are interested in is computing the sound power. So we do the measurement of the sound pressure using the microphones, and then we'll multiply with the area of the hemisphere to compute the sound power. What we'll get finally as a result is one single number for the sound power level, and that is what is commonly reported for certification purpose. In this sound pressure based sound power measurement, what we have to do is we have to use this equation to do the calculation for the sound power. The left hand side LW, that is the sound power level, and that is based on the measured average sound pressure level. This LPI corresponds to the sound pressure level that is measured at these different microphone locations. So as I said, they can be in the form of a hemisphere or a parallelepiped like you see here. But the important thing is also that they have to be uniformly distributed. Ideally, you want to do the measurement in an anechoic room, so the rooms are specifically treated with noise absorption material. But a lot of times we don't have the luxury of doing the measurement in anechoic rooms or semi-anechoic rooms. So in that case, we may choose to do the measurements in a hard wall test cell, let's say, for example, hard wall. But this ISO 3744 allows to apply some corrections to account for the room environment. There will be reflections from the walls, so you have to take that into account. And also there can be some background noise. And to correct for those, there is this K1 and K2 correction factors that we have to apply to compute the actual sound power of the test object that we are interested in. This term here represents the average sound pressure level. Now, as you could imagine, in a hard-walled cell where there can be reflections from the walls, the sound pressure level that you measure will be higher than what you would measure in an ideal acoustic environment like an anechoic chamber. Reflections from the walls and the background noise, you correct for those using this K1 and K2 correction factor, and then you take that area into account, the surface area of this hemisphere or this parallelepiped, and then compute the sound power based on that. The recommendation is that in terms of the background noise, it should be 15 dB lower than the sound pressure that the object that you're testing generates. The background noise should be at least 15 dB lower. But if it is between 6 dB to 15 dB lower, then you can correct for that using this K1 correction factor. This K2 correction is for the room environment. The reflections from the walls causes reverberation in the room. So this K2 correction factor is to account for that. If we look at the standards 3744, 3745, and then there is a 3746, they are similar in terms of the measurement of the sound pressure to compute the sound power. But this 3744 is engineering grade. 3745 is a more precision grade. And 3746 is not commonly used in the engineering context, but 3744 is the one commonly used. 3745 is a more precise way, but the requirements are slightly different for which standard you follow. In 3744, background level should be 6 to 15 dB below the noise source. Not ideal, but we can account for that with the K1 correction factor. 3745, it is the precision grade. The requirement is at least 10 to 15 dB. The background noise should be lower than the noise source. And so with this precision method for ISO 3745, you get more accurate answers. That is the advantage with the 3745. It is commonly done in the semi-anechoic chamber. 3744 can be done in outdoors or even indoors with the hard wall cells. So we're talking about the K1 and the K2 correction factor. K1 is called the background noise correction factor, and the K2 is the environmental correction factor. We are going to look at these two shortly. By knowing what the background noise is, you can correct for contribution of the background noise to the measured sound pressure and then correct for it. And similarly, K2 correction factor, you have to do measurement for the reverberation in the room, and there are a couple of methods for doing that, but you have to account for that in the calculation. This picture shows different arrangements of different microphones. The black dots correspond to the precise location of where the microphones have to be placed for this ISO 3744 standard. And it can be in one corner of the room, or as hemispherical arrangement, the source is at the center, or cylindrical pattern. Different arrangements are possible. So what makes sense in your situation will be dependent on what type of facility you have. And based on a preliminary set of measurements, you can determine whether that is adequate or not per the standard. Here is another picture showing a different arrangement of microphones in the hemispheric arrangement. And you can do this type of measurement in an outdoor or in a hard wall cell, or even in something like a semi-anechoic chamber also. I specifically show this picture because here we have a reference sound source. That is a source that generates a known amount of sound power. From the specification sheet or the calibration sheet for that reference sound source, the manufacturer of that sound source will provide what is the sound power in a controlled environment in their lab conditions, acoustically controlled environment. That will be in ideal conditions for measurement like anechoic or semi-anechoic chamber, and then at a certain temperature, pressure, and relative humidity, all these factors can play a role. So they give us that, and then what we can do to characterize the environment, we can use that same reference sound source in our environment where we measure, and then we compute the sound power from that and compare that to what has been reported by the manufacturer of that reference sound source. We find the difference between the two and then apply that correction based on that. If you think in terms of the following the ISO 3744, like what you have to do, you have to measure first with the source of measure some background noise. Source meaning whatever you are testing, that is the source. And when it is off, you measure that background noise, and then you have to apply the K1 correction factor. You also take a reference sound source, a source which generates known amount of sound power. You do the measurement with that. You apply K2 correction based on that. And then you measure the arrangement with your microphone array, spatially arranged like form of hemisphere or parallelepiped. And you have to correct for this K1 and K2 correction factor, and then do the correction for the surface area, take into account the surface correction, and then finally from that you get the sound power. When you measure the background noise and you check whether it is meeting the requirement of the background noise between 6 to 15 dB lower, if the background noise is only 2 dB lower, then this method is not suitable. But if it is between 6 and 15 dB lower, then you can use this K1 correction factor. If the background noise is less than 15 dB, then you can just ignore the background K1 correction. Once you have the average sound pressure and you check the K1 and then apply the K2, then you can do the surface correction to compute the sound power. Okay, with that background information, basically measuring of the average sound pressure level, and then I want to apply K1 and K2 correction factor. Let's see how to do that in TestLab Neo. As you may have heard, TestLab Neo is where most of our development work is going forward. What you may have been using in the past is called TestLab Classic, but then more and more features are being added, and TestLab Neo is getting more capabilities, and it is a new interface. It's a very exciting interface. It has a lot of features which can make your life very easy in terms of the data navigation, plotting, reporting, and things. And with TestLab 2506, which was just released, there were some new capabilities added specifically related to the sound power. So let's take a look at how to use TestLab Neo for the sound power calculation. So I'm going to my TestLab 2506, and then I'm going to launch Desktop Neo. To give a little bit of background, I have already some measured data of this background noise in the room, and also we have some measurements of the sound pressure using 10 microphones in a non-ideal environment, I would say. So we have to apply the K1 and K2 correction factor. We'll see how to do that in TestLab Neo. So there is an add-in specifically that we are going to use called Sound Power. The way I'm starting it, I'm starting from scratch so that I can navigate you through the process of how to use it step by step. Okay, I need this add-in for Sound Power. And so if I go here to File, Add-ins, and that is where I have added in this Sound Power. This add-in requires 19 tokens, and it is specifically meant for the sound power calculation. Now you may notice that I have added a couple of other add-ins. Let me see. This process designer is used for doing the calculation by following a certain process that goes with the sound power. In addition, I added signature analysis. Let me remove that for a moment, and then I can add that later. Okay, so desktop, I am in TestLab Neo, like you can see at the top. And then I have some data, and what I do is typically I'll go browse to the data, and then if I find something, and what I do is I add to quick access list. And what that does is it creates a shortcut like the one shown here on the top left hand side, like SoundPower Neo. That is so that I don't have to browse through this whole tree every time. If I add it to the quick access list, I can easily access the data. Okay, so there I have it. I have a TestLab project with some data. So if I see this, there are different sections within this project, and one of them is for background noise, and I can see here there are 10 microphones. I can view them. There is a time history for these, and I have that data. Now notice in TestLab Neo, this is really a cool feature called the pivot table. what you see commonly is something like this, which is called a list view up here at the top. But if we change to this pivot view, we can see what type of data it is and all the microphones listed in an easier way, I would say. So for example, here there are time histories, but if I click on this section for background noise, then I can see what are the different types of microphones and what do they have. They have spectrum and auto power and time histories, so that I can easily navigate through the data efficiently. So here I have the background noise measured in terms of the 1/3 octave spectrum. And when I click on it, I can see the 1/3 octave level for this microphone. This is the background noise level. So it is about 30 to 40 dB across the frequency range. And as I go through it, now I can see how the 1/3 octave spectrum changed for the different location. And I have the average background noise also, average of all these. And then I can look in terms of the auto hours also. Now I'm showing this to give an idea for the pivot table, because it summarizes all the data that you have in one section or one project, all in this nice tabulated view, so that you can quickly navigate through the data. So what I'm going to do is I'm going to take this background noise data, and I'm going to start with that, and I have to first compute the average background noise as a function of frequency. I'll put this throughput in the input basket. So I right click on it and add it to the input basket. I have 10 microphones. When I go do this, I have in the input basket, my data is there. And then I will go to this processing tab at the bottom, and I'm going to process this data. As it so happens, there is a method, what we call a method, available for calculating the background noise. And that got added because we have the sound power add-in. If I'm looking for a particular method, for example, if I want to calculate auto power, then what are the different methods associated with that? It will show us all of them. And what is the required add-in for that? It tells us. So for example, if I want to calculate the spectrum average, I'll need the signature analysis added. In this case, I want to compute the background noise level. I'll just see that here, and I see that the sound power method is already added in. So that's why it is not grayed out. Unlike this one where it says extract background, there is another method that is used by our NVH simulator add-in. So because I have not added that in, that is still grayed out. So once that I have added that in, I can use that for the calculation. But what do I do here? I don't know, honestly, let's say. Then I can go here. I can click on this documentation for the properties associated with this. So when I click on that background noise level method, I can click on that, and I can click on this documentation and what it is asking me to check. So what it is looking for is input is time history, and the output is a block like a spectrum or an average spectrum. And you can compute that in terms of first octave, 1/3 octaves, or auto power. And you can specify the lower and upper frequency range that you want. So with that information, basically, if I need to use the time history data, then I can connect them to calculate this background noise level. And I want to compute in terms of 1/3 octave. I can also compute in terms of auto power and the frequency range. And here I have to specify the channels that I want to use for this. Now, in our case, there are 10 microphones. They are spread in the room, uniformly distributed. And we want to compute based on the time history data that we have for the background. So if I click on that, I can specify what data I want to use for this calculation. So we see that there are 10 microphones, and this is ISO position 1 to position 10, and I'm going to add them, select them, and use them for the calculation. I have two options here. I can calculate this average of all the 10 microphones, or I can calculate the background noise per channel. We can do both ways. Why is that important? Is because the ISO 3744 requires us to calculate the average of all the 10 microphones, whereas ISO 3745, you have to take each channel separately. You have to do the background noise correction for each channel. It is a precision grade ISO 3745, but basically the point is that you can do it both ways. And as a matter of fact, what I'm going to do is I'm going to calculate both ways. I will add the same data. This is the time history data. And then this one, I'll call it per channel. So I have the background noise set up. I will give it a name, background noise average. I can give it a name like that, or I can go here and say background noise channel. So BGNCH. Okay. So we have two calculations going on here. Okay, so then I'll do the calculation, I'll run. Then it does the calculation. You can see the progress bar. It does some calculation. And now we can see what we got. So then I can hit accept or reject. But because I didn't specify a name, let me give it a name. I can say background noise calc. I can give a name like that. And I click on the run button and I can do the calculation. So, and then I will hit accept. What then happens is that within this project, I can go navigate through that and find the data. So this background noise calculation, I have the 1/3 octave spectrum as well as the time histories. I'm going to look at the spectrum. And I have the average background noise. So we calculated the average background noise per channel as well as for each channel individually. So we have that data. I'm going to save this project. Okay, I'm going to call it demo. Okay, so once we have done this background noise calculation, we can use this background noise spectrum to do the calculation for the sound power. So next, I want to go use the operational data to do some calculation. For doing the correction for the K1 and K2 correction, for the K1, we need a background noise. And then what TestLab does is based on the measured operational data that is with the object under test when it is running, then it will do the correction for the K1 by looking at the background noise. For the K2 correction, there are two ways to do that. We have that measurement also for the K2. And what we have done here is that for the K2 measurement, for the K2, we have the sound power of the reference source or the calibrated source and what was provided by the vendor. So using these two pieces of information, we can compute the K2 correction factor. If you don't have the K2 measurement data that you have, if you have not already calculated the sound power for that, then you can basically use the sound power method within the sound power add-in to do this calculation also. So within the sound power add-in, we can see that there is a sound power level method and then the sound power map. The sound power map is to generate the color map. So now that we have computed the background noise, let's take a look at computing the sound power level. I'm going to start a new process here. I don't want to save it. I can just say no. And then I want to compute the sound power from that. So now for sound power data, we cannot use that background noise data. Now we have to actually use some operational data where we tested with the unit running. So I have some throughput data from that, right? I can take a look at the time history. I have 10 microphones here. I'm going to put this in the input basket. So replace in input basket. So the input basket will now have the operational data that we'll use for the computation of the sound power. Okay, so what we then go to the processing, I'll connect the input data to the sound power level method. And here we have the selection for ISO 3744 versus 3745. You can apply some weighting. You can say you want to calculate 1/3 octaves or full octaves. You have that option. You can do 3745. Okay, if you go to 3744, there you go. And then you can specify the range and you have to specify the area of that measurement surface over which it was measured. In our case, I know that area and that is 6.28 meters square, right? So I specify that. Now this pressure data here in this case is the microphone data that I have, and I'm going to put that, select that data using all 10 microphones. And then this K1 correction that I want to apply the K1 correction, it gives the option to apply it on the average or per channel. Let's say you select average. So that means that I have to provide the average background noise. And remember that we already had the data and we computed that. So I'm going to go to this TestLab section and I have this background noise calculation run. So I'm going to get that spectrum from there and I'm going to select this average and then use that. There you go. It's there now. Similarly, if I want to apply this K2 correction factor, I have options here. I can use the reference sound source method or the reverberation time method. So if I select the reference sound source method, then we have to specify two curves here. One is calibrated reference and one is the measured one that you have. Calibrated reference, that is the one as provided by the vendor of that reference sound source, and what we have measured in that environment. We have to specify both curves here. And when we do that, it comes up with this window, and now again I can browse to that location where I already have that data. So I go here to my project here, and I'm going to select the specific curves that I want to use. So in this case, I want this calibrated one. I will select that, the sound power from that, and then I'll select the reference one that I measured in my environment. So there you go. I'm going to that particular location and I'm going to select it. Okay. So if you wanted to apply only K1 correction factor, we could have selected none here for K2 correction. So that is also possible. And then I also want to compute this thing called directivity. And directivity tells us which of the measured locations is the loudest among the 10 microphones. That is, in which direction is the sound getting most emitted. So it gives us that information. Here I have specified ISO 3744 and the required data for it. Now I'm ready to do the calculation. And I'm going to say, so this is sound power and the 3744 standard. And then I'm going to say my K1 correction is average, and then K2 is reference sound source, like that. And I click on the run. Then it will do the calculation and show me the results from that. Now, before even accepting the run, the results are temporarily stored in what is called active analysis. So if I click on active analysis, then I can see that there is some sound power levels and all this data that is computed. And I can check whether all the data that I need is computed or not, right? Sound power spectrum. I can see that the sound power is calculated. There you go. I have it and it looks good. I've done my check and I'll say just say accept. Then it gets saved in the project, and I'm going to save this project again. So now we have this sound power 3744 with the K1 and K2 corrections applied. So you can see that it's very easy to apply the method, and then you can apply the K1 correction on one channel or multiple channels, or the average or per channel basis. You have both options there. If you compare to TestLab Classic, we didn't have the correction per channel. It only supported 3744 standard, not the 3745 standard. Now, if I want to do the same calculation in the 3745 standard, I can do that selection. Again, I have to specify the area and which microphone data that I want to use. But then this K1 correction, now I have to specify per channel, and I can select the data that I've already computed as part of that. So sound power, and then I have per channel, and then I'll select all of them and then select that. For the K2 correction factor per the ISO 3745 standard, in fact, we have to specify the temperature, static pressure, and relative humidity. That's the way K2 correction is applied per the ISO 3745. We cannot do this in TestLab Classic, applying this K2 correction per the ISO 3745. So that is another reason for you to use TestLab Neo for this. So I'm going to change this run name and say this is 3745 standard, and then I'm going to give K1 average and K2. I'm applying the K2 correction, but that is not based on reference sound source. So I can just say click on run, and then it does the calculation for me, and then I hit accept because I know the data is going to be okay. So now I'm going to go to the desktop, and I can look at the first result. Let's say this K1 sound power, and what I see here is that there is a lot of data available here, and we can see that sound power is one of the calculation, and we got that. In addition, there is an option to calculate the overall sound power, and that we can show also. It's just a single number. It also gave us this K1 correction factor and K2 correction factor, and that information is also stored. And this level difference shows that what is the difference in the level between the background versus when the source was running. And we can see that, and if you think of add single cursor X and single cursor Y, if you want to check how much data is below 15 dB difference, we can see that there is a correction factor that needs to be applied for that. And we did. And if you look at the K2 correction, we can get similarly the calculation for that. And ultimately, we are interested in the sound power. and we calculated the overall sound power also, and that is nothing but if you put a double cursor and if we cover this entire frequency range, it just gives a singular value. We can calculate the RMS. It is 87.75 dB, and if you do the same thing for the overall sound power, we get the same answer, 87.75 dB. All the information is there for you that you need for making an assessment of the overall sound energy radiated. One other thing nice about Neo is that it gives us the information about this directivity index. I'm going to create this display called function map display, where I can display all these directivity curves. And in fact, first let's take a look at them. This directivity tells us how much a certain microphone location, for example, this position 1, how much is its level compared to the average of all the 10 microphone location. And so here you see that at this frequency, this is 0.87 dB more than the average at this frequency at this location. Whereas at another frequency, at 160 Hertz, it is lower than the average. Or if you see here, the average 3.13, it is higher than the average. So basically, you can get an idea for which direction the sound is radiated based on the frequency and the position of the microphone. And if you create this function map display, you can drag all these curves and put them into this display, and it tells us at what frequency, at each frequency, which microphone is the most active. So this directivity, it's saying that at this frequency, with position 2 is the most sound is getting radiated in that direction. Now you have to know what that position 2 corresponds to. But once you know that, you can get an idea for what is making more noise. If you take a generator, is it coming from the engine or radiator, whatever, or the fan, you can get an idea for that. So this is something new in Neo, and it's not available in Classic. So that is why I would say there is a lot of different reasons to use Neo for this type of processing, because it makes it very easy to do the calculations, and it takes both the K1 and K2 correction factors and following both the ISO 3744 and 3745 standards. In TestLab Classic, we couldn't do the 3745 standard, but now in Neo we can do that. And the directivity maps, they are calculated also, and they can be helpful in terms of how the sound is getting radiated spatially. And the sound power maps can further be used for processing order sections, overall level map statistics, frame statistics, and all. With that, I come to the conclusion of this presentation. I really appreciate you listening to this presentation.